All right, Mike Wimble, go ahead.
Well, not sure I recognize which thing I should be sharing here. Oh, there's more. Oh, wait, there's more. There we go. But not that. The hell, man?
You gotta love live demos.
Yeah, maybe I need to get this back to the right screen here. Why can you not see my screen?
We're seeing the NAV2 local planner screen.
Oh, you are? Oh,
Yes,
okay.
it works.
Let me go share that again then. NAV2 local planner, share. And that's what you see.
Reviewing your screen.
You see the NAV2 local planner. Okay.
Yes.
All right. So for weeks now, I've been trying to tune my robot, both in simulation and in the real world, to navigate, tight places and avoid objects and inappropriate places and things like that. And I almost got the DWA planner fairly well tuned, but turns out that the MIPI planner is much better for what I need. But in the process, I've read a whole lot of code. I have found, as always, that the ROS2 documentation is abysmal. It gives you hints at things, but it always leaves out the important stuff. I don't think anywhere I found in any of the ROS2 documentation that you would normally find, does it ever mention that when you get around that you have to have a list of critics and that the scales on the critics are such that the smaller scale means it's more important than a larger scale. But at any rate, let me tell you about local planners. So when you click, it's over, I gotta make sure I've written this paper twice. And yeah, this looks like the right one here. So when you click on in RViz 2 on the go to this goal thing, it kicks off a series of steps. Okay, and the thing that what it really kicks off is the behavior tree. Okay, and there is a default behavior tree that most people use. This is what the behavior tree looks like here on this. I'll expand it a little bit here and come back. So if you didn't see my talk on behavior trees from a few years ago, let me tell you how this thing works.
Wait, so you're doing something? We only see the NAV2 local planner. No, I didn't see anything move.
Oh, you don't see me
I'm looking at a chart right now.
You don't see me zooming in and out on my graphic here?
I see.
I'm seeing it that way.
Is this paper available online?
I couldn't make it available. It's in a Google Share right now. So can you see the behavior tree?
Yeah, we see it.
Yes.
Tree, but I thought you were pointing or doing something.
Okay. So the way behavior trees work is, I'll try to keep this quick part of it. Behavior trees get called with a tick function on order of like 100 times a second. And the tick is passed to the root, and every node in the behavior tree passes the tick on to the child below it and so forth. And so when you click on a goal in ROS2, it comes in, the goal is given to this recovery node here. Now, if you can see my mouse circling. And the recovery node, the way it works is it tries the leftmost thing. And if that succeeds, we're all good. If that fails, it then does the next thing in the list. So if this pipeline sequence fails, it's going to do this reactive fallback. We'll come back to that. So what does a pipeline sequence do? A pipeline sequence has a list of children, and it tries the leftmost child first until it's successful. And then it does the leftmost and the second child until they're both successful. And then the first two and the third child until all three are successful, and so forth. So this pipeline sequence is going to pass the tick down to this rate controller. That's going to do its child every second. So it's got a hertz here of 1. And so its child is a recovery node. And the way recovery nodes work is it tries the left thing. If it succeeds, all good. If not, it does the right child as part of the recovery. So this thing starting at the top says, get all the way down to the bottom and compute a path to the thing that you clicked on in RViz. And it's going to call this compute path to pose server or action handler to do this thing for you. But what it means is this thing is every second that this thing is trying to get to your goal, it's going to come back and replan the goal again. And if the goal succeeds, that's great. We come back up to the recovery node, we go up to the rate controller, we go to the pipeline sequence, and then we'll come down again to this follow path node. If that compute path to pose, the global planner fails, it does the other thing in the recovery node. It clears the entire cost map, and then it goes back and tries to compute the pose again, the global planner. And the thing above it, the recovery node, says only try this one extra time. So it'll try to compute the pose, global, a path to the global goal. And if it fails, it'll clear the cost map and try again. If it fails the second time, we're all done. It'll just come back and give you an error, say we can't get there. But assuming it found the global, a path to the global goal, comes back up to this rate controller, the pipeline sequence comes back down to the recovery node. So it's going to call this follow path action server. So this is the guy that's going to actually try to go from where you are to where the goal is. And it's given the path that the global planner came up with. And that path is a kind of suggestion. You might want to try to follow this path to get to the goal. If it fails, its parent recovery node will do just like down below. It'll clear the local cost map and try to replan from the local plan again. If that fails the second time we're all done, it'll go into this upper recovery node. And you've seen this recovery behavior before. It does this recovery fallback where it tries to update the global goal, goes into these recovery actions of clearing the local cost map, clearing the global cost map, does a spin of 90 degrees. It waits for 5 seconds, does a backup 0.3 meters over a time of 0.05 seconds. And then it goes back up to the parent and tries this whole sequence 6 times. And if that doesn't work, it fails.
Hey, Michael,
yes.
Can you zoom in and scroll up? I mean, it's like cut off and really small on my screen here.
Let's see, can I zoom in more? That's as much as I can zoom in.
I'm not seeing any change in the screen.
Well, I can suggest you look at the paper when I get done on this. It's just.
Does anybody see anything move, or I don't see a cursor?
It's zooming in and out on my screen.
All right, I'll
Same
quit.
here. It's zooming just fine.
Yeah, not sure what the problem is. Can't help it.
Sometimes the Zoom screen share's whacked.
But the purpose of all of that was just tell you that I'm just going to concentrate on this follow path.
So, hey, Mike, is this the generic nav2 configuration?
If you don't tell nav2 otherwise, if you call the nav2 normal bring up, nav2 bring up, by default, it uses this file right here. So if you look in the nav2 code thing, if you go to opt, ROS, Humble, whatever, shared, you'll see a navigation 2 directory underneath there. There's nav2 BT.
Yeah, and I don't want to get ahead of your talk, but are these parameters controlled? Are they controlled by the parameters?
Yes, you can override what behavior tree you want to use. You can take this behavior tree, this XML file, copy it to your local directory and change it. So you could decide that I don't want to wait 5 seconds after I do a spin. I don't know why it waits 5 seconds. You could decide you only want to wait 1 second. You can add nodes, delete nodes. So my talk that I gave a couple of years ago showed how to create your own behavior tree to walk around the edges of a building. Okay.
I have a question, Michael.
Yes,
Is obstacle behavior, obstacle avoidance behavior kind of taken care of this diagram as well, or is it hidden in the follow path node?
it's hidden in the code underneath. So the behavior tree is just driving big behavior. Yeah, we want to compute a goal. We want to try to follow. We kind of compute a path to the goal. Then we want to try to follow that path. That's what this behavior tree is doing. And then
But if we have an obstacle, we have to recompute the path, right?
that's done not in the behavior tree, but in the code that this behavior tree references.
So it is hidden in the follow path
Yes.
node. Okay.
Yes. Which is what I'll be talking about. So quickly, what this section of the paper says, that there used to be in ROS 1, there used to be a global planner and a local planner. At ROS 2, the local planner is now called a controller. There are several controllers that are provided for you for free. If you just take the sample navigation.yaml file that they give you, it is going to use the DWB local planner or local controller. I guess it's called DWA local planner as one of the free ones they give you.
Is that
All right.
DWB Bravo?
DWA local planner. It's mentioned further on again too. Okay, and what a controller, this local planner does is it takes the path from the global planner and it's going to issue the command vel commands to move the robot. That's what the controller does. Takes a global plan and it tries to follow it. And so it issues the command vels to make it. And you can think the global path, the global plan, the global path is just a suggestion to the controller. And the controller doesn't have to follow it, and it's free. In fact, it doesn't follow it exactly. It tries to follow it, but that's what all these tuning parameters I'm going to talk about are all about. How to make it follow the path and do better obstacle avoidance and things like that. Okay, and I mentioned in here that, the global planner, it doesn't know anything about things like, is the battery dead or is the robot about to fall over? It just takes the map typically, and it's got the LiDAR, the map typically, and it's got where you are in the map. And it does this computation to try to find some path from where you are to where you want to be without running into things that are on the map. But it doesn't typically know about furniture that's very far away from you, cats moving and things like that. Now, the local planner, the controller, it doesn't worry about everything either, but it's going to try to follow that general plan, but it pays attention to more things. The local planner, it doesn't know about battery power either. Or if you change priorities as you're going along, like if the robot's about to tip over, that's what the behavior tree is for. The behavior tree, as talked about in my earlier thing, you can put nodes in here that say if the battery is starting to run down, you can tell the behavior tree to abort everything, ooga, dive sort of thing. Go back and charge the battery, and then pick up where you left off. That's an excellent thing that behavior trees do for you. But then it'll go back to trying to follow the plan that you had before, assuming the goal hasn't changed down here. So the controller is just trying to make the best attempt possible, given the immediate robot state, that is where it is in the room, where it's moving, its current velocity, what the local sensors are reporting, and it's trying to follow that path. That's what the controller is all about. Each controller has a different way of doing it. The one I'm going to talk about here is the DWB local planner, just to pick one, because it's a default one. All the other controllers, as a rule, work similar to what the DWB local planner does, but they have a different algorithm. So when you click on the nav2 goal in RViz, which is one of the many ways you can, one of a couple of ways you can give it a goal to go to, the RViz sends a message to the behavior tree. The behavior tree starts reacting to your message, which does what I was showing you down below. It's going to take that click point and it's going to ask the global planner to form a plan, form a path to get there, then it's going to hand that path off to the controller. Okay, so skipping a bunch of, how do you get from here to there? The follow path thing is actually an action server that's lying around waiting for someone to give it a plan to follow. That action server ends up calling a piece of code called compute code. So how you get from there to here isn't particularly interesting. But here's where all the meat starts on the thing here. So I'll go over this stuff kind of quickly because I figured this all out, but you only need to know generally how it works. So this global controller in your YAML file, you specify what planner do you want to use. All right, that's called the controller. It's going to ask, your YAML file specifies, how do I tell if I'm getting near the goal? So you give it a goal checker. And by default, it's called the simple goal checker. And the goal checker is just going to say, what's the distance from the goal that the robot's at? And what is the angle of the robot compared to the goal angle you told it to be at? And if it's within a certain tolerance, it says, yep, you're there. Otherwise, it just says, nope, you're not there. Keep working on it. There's another component called simple progress checker, who checks to make sure that your robot's actually making progress toward the goal. So if your robot, for instance, were to run up against the wall and the wheels are just spinning and nothing's happening, after a certain period of time, it'll just say, you're not making progress, abort the whole thing. And when it aborts, it's up to you and your code to come up with something to do about it. So there's a progress checker, a goal checker, and the actual planner, the DWA thing, that's going to do all this. So it gets the current goal. And then there's this thing, and one of your parameters is called the controller frequency. And at the end, you'll see the complete list of parameters. So the controller frequency is how often do you want me to send command vel signals out to try to move your robot? So it's typically set to like 20 hertz, 30 hertz, something like that. And inside this function, it's just going to ask, has the global path changed? Because I want to always react to the current global path. And and so make sure it's all set. Then it's going to call this function called compute publish velocity. So what compute and publish velocity does, it simulates several techniques or trajectories toward the goal. So it's going to make up ways to get to the goal. You could consider them sort of random things, but they're not. I'll explain how it comes up with possible ways to get to the goal, and it's going to try to pick the best one. And then it publishes a command vel. And after it publishes that command vel, it says, have I got to the goal yet? And if not, it just does it all over. Make sure I've got the latest goal and try to select the best way to get there from where I am. And once you finally reach the goal, we're all done. Okay, so this compute publish velocity function, he gets the current pose. He calls the progress checker. And if you failed the progress checker, we're all done. Otherwise, he's going to call this a meaty function. He's going to compute velocity commands using the DWA planner sort of thing. And that DWA planner is going to come up with the best possible thing currently. And then when he gets the best possible thing to do, you may know that the way the command to move the robot works is an action handler, so that you tell it where you want to go and it gives you this constant feedback. I'm 2 meters away from the goal. Now I'm 1.8, I'm 1.7. So you can plug into that feedback and see what progress you're making and react to it if you want. But so this thing, every time it makes a velocity command, it publishes the feedback of what speed you're going, the distance you're at, so forth. It publishes that twist message in. All right, so again, the meaty thing is this compute velocity commands function. So the compute velocity commands eventually generates a set of candidate trajectories from the current pose. So in your YAML file, you tell it, you give it the name of somebody that'll generate trajectories, and we'll talk about that a little bit. But then you give it typically 3 parameters. You say how many how many guesses do you want to make along the X direction, the Y direction, and the rotational direction? So typically you say something like, make 20 guesses in the X direction. These are guesses to where should I move the robot to try to follow that path that the global path is all about. So make 20 guesses in the X direction, 20 guesses in the Y direction, and 20 rotations. And for every possible combination of those things, I'm going to say, if I went to one of those points, so 20 times 20 times 20, for instance, would be what? 88,000 guesses. Yeah, if I went to each of those 8,000 positions, which one would be the best to achieve getting close to that goal on this thing? And so then for each one of those potential places you want the robot to go to, it's going to compute a score for if I went there, is that a better place than where I am? Is it better than these other positions? And the way it comes up with a score, so the best score is the thing that has the lowest score. So what we're trying to achieve is find all of these XY rotation positions that result in the lowest score. And that's the best possible thing that I want to do next. And the way it finds scores is you give it in your YAML file, you give it a list of critics for each possible place. And it iterates over each one of these critics. So for all 8,000 of these potential places to go, it calls this list of critics for each one of them. And each one of those critics comes back with a score. And this iterator sums up all of these scores. And then it keeps track of what is the best and what is the worst.
What is this?
Yeah,
What
it
is
keeps
this?
track.
What is this critics thing? Is it
Okay.
code or?
It's yeah, I'll be explaining it shortly here. But it's kind of like what it says. It's critiquing that pose. It's saying, what is my opinion about this possible place to go to? Is it good or is it bad? And each one of the critiques or critics has a different thing that it considers to be good. So jumping ahead a little bit, there's a critique that says, I'm interested in being in the same, moving the robot to be at the same angle that the goal pose needs to be at. This critique is going to say, well, I want the robot to move to something that's as close as possible to the goal path. This guy says, well, I'm only interested in that you avoid running into obstacles. And there's a bunch of these critiques, which I'll talk about in a minute. So each of these guys says, I think you're doing my goal pretty well, or you're not doing my goal at all. And so we add them all up, and we say of all the possible people rendering an opinion to move to that thing, we'll take the one whose combination seems to be the best. And what you do when you're tuning a robot for the local planner, the controller.
I'm not sure I understand.
Yeah, well, good. is, they probably don't either. What you do as part of the tuning is you decide which set of critics do you want to use, and mostly you're deciding what scale, what weight do you want to assign to each critic on this thing. So, and some observations here, the critic list that you give can't be empty. Actually, it can, but if you give it an empty list, there's a default set of critics, and you may not like the default set. I think the default thing from that you're given now has a list of critics, and they.
Is it like rotate tool, oscillation, base obstacle, goal align?
Well, here's a. So
I've
here,
gone to the parameters
so
file
here's.
and I'm looking. Yeah, it's actually called critics.
Yep, and it's a list of things. So I've reformatted it here. So here's the list of critics I have. In my thing. So I've commented out the prefer forward one. I had it in there for a while. And there's some other critics I'm not using that are possible in here.
So I see these critics. Where's the critics? Where is it that you explained what the critics do?
All right, I'll come to that in a minute. All right, so the takeaway before I explain to all of them is Where was my takeaway on this thing here? All right, the list shouldn't be empty. You won't like the defaults. If you have a simple thing, it's okay, but a real world robot, you want your own list of critics. The order of the critics is not important. There are other things, like when you do the cost map and you tell it the layers in the cost map, the orders of those layers is very important. But when it comes to the order of critics, it's not important. There's an exception to that, but it's in very rare cases, and you have to know a lot about how scoring works for this to actually make any difference. All right. And what we're trying to come up with is the lowest score of all the critics. And when everybody gives their opinion, the sum of all those opinions, the smallest sum is the one that's going to be chosen. So each critic has a scale factor associated with it. So each critic generates a score for the possible, place you're trying to get to. And then the score from that critic is multiplied by the scale. So, and then that score times the scale is what's get added to the total score. So to make a critic have a greater influence, you specify a smaller scale in the YAML file. And if you want to have the critic have less of an influence, you give it a bigger scale. So this is what you do to tune the local planner. You choose a set of critics and change the scale values. Excuse me. So some critics also have other tunable features, and we're going to talk about those almost next. I'll let you look at this second while I grab a cough drop.
Wait, wouldn't it be a lot? Wouldn't the scale be bigger if you want a bigger influence? Or no, because it's a lower. It's because it's the lowest score, so it's smaller. It's a smaller scale for a bigger influence because the goal is the smallest number. Is that right?
Yes. All right, so I talk about some of the parameters, and for the first pass through this, I won't go over these yet.
Mike, I don't want to get ahead of you again, but so I see the parameters, I should say, I see the critics in the parameters file, but where exactly do you specify the scale of the critics?
So if you look at my sample thing, so here we name a critic called base obstacle. And then down below it, you'll see a YAML section for each one of these things that you named.
Okay, and so is this still within the parameters YAML?
Yes. So, and again, if you don't, there's another way to specify these values, but this is the best way to specify it.
Gotcha.
So for the base obstacle, I've given it a scale of 0.2. And sometimes there's other parameters for each one. So every critic has a scale factor in it. Some critics have other things. And I'll explain what the other things actually do. So what you're going to do in your YAML file is give it the list of critics that you want to use. And you don't have to use all of them. You have to use at least one. And then for each one of the ones you specify, you're going to give it the other parameters that you need. So each critic has a set of parameters. So I'll tell you what the parameters are up here. So, and some of them are complicated. Most of them are not. So the base obstacle. So there's two that take into account obstacles. Well, all the critics take into account obstacles, but not intentionally. The ones that do it intentionally are the base obstacle and obstacle footprint thing. So what the base obstacle critic is doing is he's trying, this is a very simple critic, is essentially from where you are to where you want to go. He goes through the cost map of all the cells between here and there. So you remember what a cost map is. It's a grid, and anything that's an obstacle on cost map has a high value, 255-ish. A free cell where there's no obstacle has a value of 0. So what base obstacle does is it says between where you are and where you want to be, I look at each of the cells in essentially a straight line between here and there, and I just sum up all the cost for it, and that's my score. And then I multiply the score by that. So if you have an obstacle along the way, that's going to get a value of 255. If there are two cells with an obstacle in the way, now you're going to have a value of, 510, something like that, so forth. So you can see that if you're nearing, and as you get closer, remember your cost map is inflated. So an obstacle has 255, but right next to the obstacle, that cell might be 254, and the next cell might be 250, and the next cell close to it might be 100, and next cell might be 10. So that cost goes down an exponentially decreasing curve. So when you get near obstacles, you incur a cost. So base obstacle is trying to say that paths that go near obstacles are bad. Paths that actually hit an obstacle, and actually what happens here, if this thing discovers that one of the cells along the way is an actual obstacle, it throws an exception. And throwing an exception is the way all these critics say, abort, abort, everything else is bad. So throwing an exception just says, this is a bad path. Okay, the next type of critic is the goal align. And so goal align has this forward point distance parameter. So the default is 0.023. And what they don't tell you in the documentation really is that this distance is from the center of the robot. How far should I go to pretend that I'm at the front of the robot, at the forward nose of the robot? And what I'm going to do is look at the angle the robot is pointing at that forward distance, at that forward point, compared to where I want to be. So it's essentially drawing a line from this forward point in the forward direction, that distance. It's drawing a line between there and the goal pose and trying to say along the goal path, actually, the closest goal path. And it's saying, if I'm sort of in the same direction that the goal is trying to achieve, that's good. If I'm the further away from that direction, it's bad. Okay, so this distance should be set to how far it is from the center of the robot to the simulated nose of the robot. Okay, there's another thing in there they don't always tell you about, or it's hard to understand if you don't see the algorithm. So in the process of walking the cells from where the robot is to the closest point on the path, it says, how do you want me to accumulate values along the way? And you can tell it, well, add all the cost by taking the sum of them, or take the product of the values of all of them. So that, the product will cause the cost to grow very fast if these are cells that, are not zero values. Or by default, it just looks at the last point in the from going here to there. It just says, once I get there, what will be my resulting angle? So most people just say, I don't care whether or not it might have been kind of good along the way. I really only care when I get to the end of what I'm currently considering, do I seem to be pointing in the right direction? So this critic score is based on how well the robot's nose will be aligned to, it's actually the closest goal path. All right, this the next one, goal distance. He's going to say, essentially, he's measuring the distance between where you are and where the closest goal path is. So, and again, you can tell it, do I want to measure up all the costs between getting from here to there, or do I just take the last point? So once I execute this, I really only care how I ended up and how close am I to the goal path. Okay. The obstacle footprint, he's a little sneakier way to do things. What he does is so in your local cost map, you can specify the footpath of your robot in one of two ways. You can either say, my robot, I want you to consider it to be a circle, and you just give it a robot radius, which is a nice fast computation. Or you can actually give it a polygon and say, this is what the outline of my robot looks like. So in either case, it draws the outline of your robot onto the cost map and then says, within the outline of that robot, this isn't actually quite true, but you can pretend it's true. It's saying within the outline of the robot, have I hit any obstacle? And if so, it's going to, raise an exception, which says this is a very bad thing. So this other thing is sort of saying, I want you to avoid obstacles by kind of steering away from them. And if an edge, I don't think this thing even looks at the footprint. I think it might only look at the radius. But it's only looking crudely to see if it hit an obstacle. This thing is looking at the whole footprint of the robot, and it makes it so that the farther away you are from any obstacle is better. This oscillation critic, you can look at the details, but I'll tell you generally what it's trying to do. So what you might find, you'll sometimes find that as the robot moves along, all of a sudden it gets into this situation where it doesn't quite seem to want to make any progress. It starts, wiggling back and forth without going anywhere, or it moves forward and back without going really anywhere. So that's what this thing detects. It actually checks, are you going back and forth within some small distance? Are you wiggling, left to right within a small number of radians? Are you doing this wiggling within a certain period of time? And this thing here says, by the way, I'm only interested in oscillation along the X path on this thing. But this thing says, if you appear to be oscillating for a while, for this period of time, then reject this path. Okay. So besides the goal align and path, which measure when you get when you sort of get to the end of everything that I'm under considering, how close am I to the goal path? This, I guess this is the goal point. I misspoke before. How close am I to the actual goal, direction and position? This path align says how close am I to the goal path, the nearby goal path, not the end point, and how well aligned am I to it? And it acts just like the goal thing. So the alignment says, how far from the front of the robot is the nose, and from there I'll compute an alignment to the goal path and come up with a score. And this thing just says find the Euclidean distance between where I am and the closest goal path, on this thing. All right, there's only two more critics that DWA provides for you. And there's a prefer forward critic and a rotate to goal. And the rotate to goal is really fascinating. The prefer forward is a thing that says, so in the parameters you give to the controller, you can specify, what are the accelerations and velocities that X and Y and Z could take on. So you can limit how fast the robot can move. And you can also tell it that the robot's allowed to move backwards. So you can say the minimum velocity for X is some negative number. If you tell it the minimum velocity is 0 or positive, it'll never try to move the robot backwards, except as a recovery behavior. But it won't consider a plan that moves the robot backwards. Okay.
So
If you have
where do recovery behaviors come in here?
that was in the behavior tree. If this thing fails to make progress, toward the goal, then
Okay.
the recovery behaviors get activated.
Critics is about making progress to the goal and the way that's done and so forth,
Yes. It has nothing to do with the behavior tree.
as opposed to recovery behavior. Okay.
Right. So this prefer forward critic says, given everything else, if I've got a bunch of things that are equally good, I want to essentially prefer ones that move the robot forward as opposed to those that move the robot backward. I've turned it off in mine. I did it for a while because when I had other tuning parameters, when you get your tuning parameters wrong, and it's very hard to get them right, actually. Sometimes my robot ended up getting in positions where if it just backed up, it would have solved it, or I wish it wouldn't back up. If it had just gone forward, it would have solved it. So this thing is all about making it so you can say that here are, and I won't explain them here, but there are parameters you can give it to figure out to scale parts of these different trajectories to say how I want to characterize whether or not this is moving more forward than another one is. Now, the rotate to goal one, he's a fascinating one because I used to always find that my robot, went like a bat out of hell when it started the path. I gave it a distant goal. The robot goes like a rabbit, zips along that path until it gets near the goal. And then when it got very near the goal, all of a sudden it just took forever to settle in to it. It go back and forth a little bit or move back and try to get a little better angle to try to match the goal post. So what this thing is all about, it says when you get close enough, when you're within this XY distance of this thing and a couple other conditions, to stop trying to move the robot around and only rotate to the final angle. So it says, if I'm within this distance and the robot is moving slower than this speed, and this thing has to do sort of scaling how far away how far away I'm from the right direction on this thing. Then I'll use this slowing factor to apply a final measure for how far away I am from the desired angle on this thing. But anyway, this rotate to goal can make it so that when you're near the goal, when you're close enough, just quit farting around and just turn to the final angle on this thing. So there's an explanation about how this works, but it's kind of tricky. If you're using holonomic robots, things that have the mecanum wheels on them, you can find that those things just end up wiggling a lot. And there's another critic available that, stops the wiggling for holonomic robots. If it's a non-holonomic, like a differential, that's not going to help you any on a thing. So now we go over quickly, but these are all the parameters that are just for the local controller. That not all of them are given to you by default. So I've gone through all the files and figured out what all the parameters are, because a lot of times they just rely on using the default values. So I like to specify all the values because, sometimes you're going to accept a software update and they're going to change the default values on you and your robot's not going to work. And you have no idea what went wrong. I didn't change anything. So I always override the defaults on everything. So I know my behavior is going to be stable. All right.
So what are we're looking at parameter files here? Is that what this is?
Yes, this is the navigation YAML. So this is the complete set of parameters you can give when using the DWA local planner in your navigation YAML file. Okay, so these first set of parameters have nothing to do with the DWA. All controllers are going to use these set of parameters. Okay, then some of the ones later on, again, aren't specific to the DWA, but I'll tell you about them too. So this first parameter, controller frequently, is how many times a second do you want me to do this algorithm and attempt to send a command val? So if you have a slow processor, you're running a heavily loaded Raspberry Pi, you'll keep getting these messages about, failed to meet the control frequency. You asked it to do it 30 times a second and could only do it 9 times a second. There's nothing bad, but it's just telling you that you expected this to happen, but your processor is just too slow. And depending on the velocity of your robot, that could be a very bad thing. If your robot is moving fast and you're only able to generate commands once a second, that robot's going to smash into things before something can come along and realize you're about to smash into it. So generally, you want the control frequency to be that your robot can't go very far before it's commanded to stop, if something happens. So you just figure out if your robot can go 20 meters a second and it's only issuing commands once every twice a second, your robot can go 10 meters before it's told to stop. So you figure out what your safety margins are on here. So this is telling you really it's kind of the name of the handler. So you will always use follow path. You don't have to. So you can actually you can actually have a bunch of different planners out there. And you can say, when I'm strafing across my garden, you know, I want to use this outdoor planner that's using GPS. And when I get within sight of that cone, I want to use a completely different kind of planner. I don't want to use this outdoor one. I want to use a MIPI planner or something. And there's a way of doing it, which I'm not going to go into on here, but you can give it a list and you can switch which one you want to use in the list. Okay, this thing is a thing that says if the planner fails for this much time in a row, you know, just consider the goal unreachable. All right, so you remember in the beginning I mentioned you have to give it a goal checker. And one of the goal checkers that they provide is a simple goal checker. So you can give it parameters down here, and I'll cover this quickly. You're also going to give it a progress checker to check if you're making progress. Here's one of the ones that are built in, which we'll talk about. But you have to tell it which goal checker do you want to use, which progress checker do you want to use, what topic. So it should subscribe to get the ODOM things from your robot. These things here are to get rid of noisy output. So if the command vel has an X velocity that's less than this value, it just sends it out as 0. You know, if the Z velocity is less than this, it just sends it out as 0. Mine's a differential robot, so it never sends an X velocity or Y velocity. So it doesn't really matter what I stick in here. You are allowed to analyze where the robot is in the world, and you can tell it that as I, for instance, get near certain objects, I want you to change the speed limit for my robot. You can write your code and this thing will respect it, but it's just saying, if you've done it, here's where the topic comes to tell me how to change the speed limit. Normally, ROS2 runs all these things under one process so that the communication between them, this is a whole bunch of pieces. You know, there's the B tree handler, there's the global planner, the local planner. There's half a dozen or more separate processes doing all this stuff. This thing by default runs them under one process, which makes under ROS2 the communication really fast between them because it doesn't copy any message. It uses shared memory. If you want, you can say, well, I want this controller to have real-time priority, in which case you've got to make these things run a separate process, and you tell it here that that's what I've done. This thing is going to run as a separate process, and it's going to have a separate priority to deal with all of this. All right. And almost everything in the YAML file has to know whether or not you're running.
Do you know what the edit of limits.conf looks like?
I used to, you could look it up, but you have to do a couple of things to allow real-time priorities on your Linux. So it's not hard to do, but there's several things. Mike, you know, Fergs probably knows this off the top of his head.
Sorry, what was the question?
Ahead. Do you know how to allow real-time scheduling under Linux?
It's a brand new feature in Jazzy. So you have to be on, I'm pretty sure that's only supported in Jazzy. You really, if you look on the wiki there, it has the thing. Basically, you drop in like a one-liner, I think, in limits.conf that basically allows that particular process name to change its level. And then the code is already built into nav2 and just does it automatically.
Okay. It's mentioned in Humble, but I didn't look into it to try to do it. I actually tried to.
It got some backport. It's been advertised as a new feature in Jazzy. So maybe it got a little bit of backport, but it was developed for that. Or maybe it's only that it's full support in Jazzy and like only partial in that in the earlier releases.
Well, when I tried it, it didn't make any difference. So I gave up on it.
What is it giving priority to here? The navigation node?
Yeah, so what it's basically doing is that you can do sort of a soft real time where you basically set the priority of things. So effectively, say you've got like a web browser open and it's consuming a lot of CPU, it will basically the kernel will pause your web browser to make sure that your nav node runs, right? Because you give it a lower priority. Actually, again, it's inverted like the other ones, right? It's like a lower priority number means that it runs first, I believe is the correct version.
Yeah, but you also need basically the real-time kernel for it.
You do not need a real-time kernel for this.
No.
This is just so that's why I'm saying it's very soft. It's extremely soft real time, right? It's not
hard
truly
real
real
time.
time. You're basically just setting the priority. This is actually a long running hack that many robotics companies use. I mean, I was doing this at Fetch in like 2015, right? And basically, if at some point your CPU is going to hit 100%, right? Like every cycle is used, this will basically say who has priority to keep running, and the things that have a less priority will basically be paused for a moment, and then they'll get to run later when there's available CPU cycles. But what it does is it makes sure that, like, especially if you like set up your drivers and nav to have better priority, then they'll continue to run while other things, maybe some background tasks and whatnot, those get paused and wait. And so it gets you closer to getting that 20 or 50 hertz, whatever it is you're doing, more repeatable, even when your system load is changing.
So for UCamp, unless you study how the Linux scheduler works, and then study how real time works, I wouldn't fart with this at all. It can cause your system to appear to be totally dead on here, and you won't be able to fix it while this is happening. One of the other things you can do in Linux, which I did when I worked for the New York Stock Exchange doing high-speed networking, is you can take these nodes and give them a whole CPU and say, this is the only thing that can run on this whole CPU. Fuck everybody else. This process runs on this CPU, nobody else can. And that's another way to guarantee high-speed response.
That's perfectly fine when you have a couple of cores even on a Raspberry Pi 4.
No, you don't do it on a Raspberry Pi 4.
You essentially assign a core, or what Linux considers a core. For hyper-threading Intels, it's basically half of one, but yeah.
You actually also, when you do that, you need to know what the memory model is. Also, I'll come back and look at these chats later on. So, Linux or Intel has a bunch of different intercore communication memory models, and they affect how this all works too. So, going further down here. So, here's what most people use for the progress checker. And it says that if in 3 seconds, I don't find that your robot has moved 0.2 meters, then I'll consider your robot as not making progress and I'll abort the whole thing. The goal checker says that if you are within 2 inches and have moved, I think this is 5 degrees in my case here, or you're within 5 degrees of the goal and 2 inches of the goal, then consider yourself to be at the goal. Okay, that's what the goal checker is all about. Okay, so now we get into the DWA parameters, and even the DWA has subparts to it too. So there's a part, so I was telling you that this thing generates these paths, potential places to go. So one of these things is the kinematics generator on this thing. So here you're telling how fast do you want to simulate movement? Well, in the planning part, it actually controls how fast you can act. Since these plans are either accepted or not, this actually affects what will the actual speed of the robot be when you do things. So on mine, I say that the robot can go no faster than 2.5, can accelerate no faster than 2.5 meters per second squared. There's also a velocity. It can't go any faster than 0.5 meter per second. So you generally find these acceleration limits are symmetrical. So there's an acceleration limit, and then a deceleration limit. It doesn't have to be that way, and I don't know if my robot actually can symmetrically accelerate and decelerate. And I don't know if these are good parameters. What you'd have to do is write a program that actually smashes your robot around and then actually measures its real-time performance to see what it could do. And then you reduce it down for safety margins. So in my case, I'm really I want the accelerations not to be high because otherwise it jerks your robot around. And I've had parts fall off my robot because it just slams the motors hard. So I've reduced the accelerations and decelerations on it. And then I don't want the robot to go faster than I can catch up to it. So, half a meter a second, I can follow it around the house, sort of thing. And then there's rotational, velocities too. And I'm saying I forget what this thing does. I think this is only for holonomic robots. But here I've told it you can go backwards very slowly if you need to. This doesn't affect non-holonomic robots. And I forget if this is actually used in the kinematics planner. I think it is. But again, it's one of these things about when you're that far from the goal, consider you're at the goal.
Mike,
Yeah.
you're saying the robot's allowed to go backwards. This is in the course of navigating, not recovery, right?
Yeah, the recovery has a backwards recovery action, and it ignores all this.
I got you, but this is in the space of actually navigating.
Yeah, well, it's moving along the path. Yeah, well, it's moving along the path. It could decide, a cat jumps in front of it, it sits in front of the robot's licking its paws. This thing says you are allowed to plan a path that goes backwards to go around the cat. If you don't do this and you appear to be in like a box canyon, this thing will just fail. It says, I've looked to the left, I've looked to the right, I can't go anywhere, and you've told me I can't go backwards, just give up.
Typically, robots go forward.
Yeah. This allows it to go backwards, but I didn't want it to go backwards very far or very fast on this. So this thing publishes a whole lot of topics if you want it to. So when it wants to make a plan, it starts out by taking the local cost map and it projects it onto the global cost map because the actual place you want to go to was a place you click to in the global cost map. So it transforms the local cost map onto the global cost map. And it says here, would you like me to publish the resulting transformed cost map so you can see it? I said, no, it's only for visualization. It takes time. Who cares? Do you want me to, I'll come back to that one here. This one says, when I'm making all these guesses, the 20 X's, 20 Y's, 20 Z's, do you want me to publish a topic that shows you all those places and orientations it could go to? If you say yes, there's a topic. That'll show you all that things that are being considered. And you can see where it doesn't publish things into the areas like where there's obstacles and things like that. Would you like me to publish the evaluations of each of these trajectories? And it's kind of an interesting thing to look at. And I forget the difference between, I think the evaluation is a text file that explains, how it scored everything. And you can look at it, and it's a lot of stuff. But if you're trying to figure out, well, why didn't it work the way I thought, you might find information there. This thing here will publish sort of a colorized map of all the different places it could have gone, and it'll show you whether or not it thought it was good or bad on the strength of it. But all of these things are mostly for visualization. And this thing says, do you want the published global plan and local plan? I forget what global plan does, but the local thing, again, it's just for visualization. Do you want to be able to see this in RViz on here? So the guy that generates all the possible different places to go, here are his parameters. Well, actually, there's this guy. that says, how many samples do you want me to do in the X direction, the Y direction, and the rotational direction? And this thing says, do you want me to generate each of these things by using time or distance? So if you say do this by time, it takes this amount of time and it breaks it up into all the different places you could be. So this thing says, I'm going to generate 2,000 possible points. It breaks that simulated time into 2 divided by 2,000. So 1,000, 1 millisecond travels. And then it says, I'm going to generate every millisecond a new point. And if you set this to false, it says, well, I'll do it by distance. So I'll take the size of the cost map, break it into a 20 by 20 grid, and I'll make each potential point on one of those 20 by 20 places at the cost map, so forth. So a lot of these things you really don't care about. These things work well as given, unless you're dealing with tiny spaces, or huge spaces, and you don't want to spend a lot of time computing things. Most of my stuff is done on a 2-inch square local cost map, because I need that 2-inch granularity to get through tiny passages. If you're outdoors, you might want to use, a 1 meter square cost map or something. So skip all the rest of those. I make some comment about them. All right, so this thing, the documentation indicates that this thing is published to a topic. It's not. It's actually, if you turn this on true, if this thing fails to generate a trajectory, it'll generate an error message to the log file. Okay, this thing only has to do with how all these things are generated into the parameter namespace. You can ignore that. All right, so when this thing makes a plan, it takes the global plan and it says, well, I'm the local cost planner, local cost map, or the local planner. I'm only interested in things that are bounded by the local cost map. So if you remember, your global cost map is usually as big as the world, or as big as the world you're interested in. The local cost map is usually much smaller, like maybe 2 meters square. So when it looks at the global path, it says, I don't care about things that are outside my cost map. So it's going to prune that global path to fit inside the cost map. And it also says, I can do some additional pruning for you as well. And one of the things it can say is, well, I might be already close to that some point on the cost map. So the cost map might have told me to start a meter behind me, and I'm already a meter ahead of where the global plan was. And you can tell it here that I want to prune, everything that's more than, a tenth of a meter behind where I already am. And anything that's more than a meter ahead of where I am, it prune that off the cost map too. Because, the thing's only going to plan for a tiny distance anyway. I really don't need to know about cost maps that are, or the path that extends very far. So these things are just making the thing go faster. So it's telling you, do some pruning, reduce the plan that you're trying to achieve by a bit, just to make it go faster if you turn this on true. And Steve Machensky says you should always turn this on true. There's no real reason why you would ever make that fast. And then these things here, you really only tune them if you're running out of time on your, when you do your looking how fast everything's going. These are things that can do, along with the size of your cost map and the resolution. Those are things that have a big effect on how fast this thing runs. This thing here says that, remember how I told you it iterates over all these critics and sums all the things together? Well, the summing thing, normally a critic can only return a positive score. As it, each one of these little places it can go, it returns its score and then multiplies it by the scale. And it sums all those things together. Well, most critics can, in fact, I think almost without exception, these things can only return a positive score. This thing, if it's true, says as you're summing up these critic scores, I've already chosen what I think is a good place to go. If when I'm summing up these things, your score is already bigger than the best one I've got so far, just ignore trying any further evaluation. Just go on to the next one on this thing. So normally you would leave that on too. If you have a critic that could actually generate a negative score, you might say, no, you need to evaluate all the critics. But again, turn it true might save you some time. This thing says when you transform the plan from the global plan into the local plan, the local cost map, do you want me to shorten it? Yeah, you'll always do that too. This is one of the pieces of code they give you, unless you're going to write your own, do that. So this thing's kind of important. If you have pretty much the only thing this thing is looking at is the cost map and the ODOM data to do the planning. So the cost map's already incorporated things like the LiDARs and the sonars and things like that. So it's given the cost map. It knows where you want to go. It wants to know what your current velocity is, because that affects, how fast I'm going to be achieving to the next point, so forth. So all of these things are time stamped. And when it looks at data from the cost map or the ODOM or anything else, it says if the data from those things is more than 0.3 seconds older than now, just ignore the data. The data is out of date. I think the default value is 0.1, but if you're running on if everything's running on one processor, like you're running this all on a Raspberry Pi, and you're finding that the Raspberry Pi is heavily loaded, your sensors might not be reporting fast enough. It all has to do with that scheduling algorithm, all that. So if you find data is being ignored, you increase your tolerance. The downside for this is that it means it'll accept data that's out of date. The truth isn't quite up to date. So it's kind of a balancing, but I've always found that 0.3 just works fine for me, even on slower processors. All right, so, and then here's the meat for this. So give it the list of critics you want to consider. And then for each one, here are their parameters. If you don't include the parameters, there's a default that was given on that description I gave you before. So base obstacle, to me, is a very important thing. I want this thing like hell to avoid running into things. So it's got a very small scale. And I probably could tell it, I think if you turn this false, it uses the product instead of the sum, but sum works fine. The goal line and the goal distance, they're vaguely important. I want the guy to try to eventually get to the right place, but it's only slightly important. So they have a higher scale. And my robot has a diameter that's about, from front to back, it's like 0.23 meters. And actually need to make this a little more accurate. When I took a snapshot, it was like that. So this is the distance from the center of my robot to the front nose of the robot. So this obstacle footprint is another guy that's pretty important. He's checking the whole footprint to see, I would like to say whether or not it encloses an obstacle, but actually what it does is it draws lines around the edge of your robot, and it checks to see if one of those lines intersects an obstacle pixel, which isn't quite the same thing, but it's close enough. Okay, these path lines are more important than the goal lines here. So the path line, these are the guys that are saying, how close do you want me to follow that goal that was given to me by the global goal planner? So in my case, my biggest problem is that the robot doesn't spin fast enough. It tends to want to gradually steer itself to follow along that goal thing. And I want to steer pretty fast to try to get to that goal path. So I've given it a lower number. I want it to try to stay close to that goal, because when I get in tight places, this thing tends to drift off because it's keep wanting to look ahead, and it says, oh, I can do a shortcut. I can cross across old, Farmer Fred's lawn and get there quicker. And I'm saying, Dad, don't be doing any shortcuts. Try to stay away the original plan we all agreed to. And very importantly, try to stay at the same angle it told you. Because you start, moving your nose around, you're going to bump your nose into the side walls in these tight quarters. I'm not using the prefer forward, but here are some scales I was using when I did it. And this rotate the thing, this is very important to me, because it was taking, geez, 10 seconds to settle in at the goal. But I say, when you're within 2 inches of the goal, and looking, well, it's actually not doing that. And you've slowed down to only moving that fast, then stop looking. Just make your final rotation to get to it. Okay, that's all of that. Any questions? Otherwise, I'll just stop talking.
Yeah, I've got a question. In Robo Magellan, what's the tolerance to the goal? Do you have to actually touch the orange cone, or is 2 inches close enough?
You have to touch.
You have to touch it. So,
And you can't knock it over.
You have to touch, but you can have like a 2-foot wide whisker on the robot, as we found out this past year.
Yeah.
That was pretty crafty. I noticed that.
Oh,
Some
yeah.
guys had these sticks protruding from the side so they could tag the cone as they were driving past.
You could spin a bit of string, like a strimmer.
well, some silly string.
That's probably the better idea than the sticks, because the sticks get hung up somewhere.
And you could
I don't
probably
know. They just had
measure
this
the change in acceleration from the spinning string to tell that you've hit it.
Do you lose points if you knock it over?
It doesn't count if you knock the cone over.
So
Okay.
yeah, that doesn't count. So Mike, and I know that many Bedouins were lost gathering this information, but I've kind of Googled around a bit, and I really can't find anything on these critics. And you've got this big long list and so forth. Even mine, I'm looking at the parameters file in navigation too, and they make mention of the critics, but I don't understand where that's being called from, where you're having, your variety of parameters for the critic.
Mm-hmm.
Yeah, I think part of that, honestly, is that the Nav2 maintainers are trying to slowly deprecate DWB in favor of MPPI.
And MPPI worked like a champ for me compared to DW.
Yeah, they're trying their hardest to make, like, if Steve could have one wish granted, it would be for DWB to just disappear and everyone to be like, oh yeah, MPPI works for me. But I think there are still some edge cases where MPPI kind of falls over completely and it's not recoverable. And so
this list of critics in the nav to bring up parameters isn't going anywhere.
Well, they only apply to DWB, right? DWB has critics, and MPPI is just self-contained.
Okay, so in this YAML file, I've referenced DWB, and I'm just unaware of it, and it's pulling these critics out of that.
Yeah, you're using, if you look at like what the name of the controller is and your follow path, you'll find that it is
my
somewhere it says DWB.
DWB_core.
Yep.
Okay.
And so you have selected that as your controller.
The
and
fact
so
I've called the DWB core means I can take advantage of these critics, and that's just kind of built in.
Yes.
Yeah, I don't know that it's necessarily take advantage of. It's you must specify them effectively in the old. So you remember DWA in Nav1?
Yeah.
DWA just had a whole bunch of parameters, and you always had to have like a goal alignment and distance to path and all those sort of things. In ROS 2, they took all of those different pieces of the algorithm and made them separate plugins called critics. And so it's modular. So if you don't want one of them, instead of just setting the weight to 0 or whatever, right? You just don't load it. Right. If you don't include it in the list, it's not there. And the big thing that allows is that apparently there were a number of people who developed closed source critics that they had to basically extend DWA. And so, in ROS 1, they would have to have just a fork of the entire DWA. In ROS 2, they could just have a plugin that's DWB.
Mike Wimble, you're using what, DWA or DWB?
DWB, I'm sorry if I misspoke and said DWB.
Yeah, everyone in ROS 2 is using DWB. DWA never got ported to ROS 2. They started with DWB.
You know, there's an important part I left out of this is, so how do you tune this? So the way I tune this is, first of all, I'm running the whole thing under simulation, but you don't have to. It just makes it so I quit running down my battery while I'm doing this. And I built a room that has a cone in the middle of it. And I sit and, tell it to go from one side of the cone to the other side, a meter away from the cone. And then I watch the path. And then I bring up RQT. And under RQT, there's a plugin that does let me change the parameters for everything that's out there. And I sit and change the parameter values one by one and see, did that improve its performance one way or another? And if so, I make a note about it, eventually move those things into my YAML file. But, I spend hours and hours and days playing around with combinations of these things because they all affect each other. Changing one affects, what happens to another one on this thing, or at least the effective performance on this thing. So there's a lot of tweaking to make this work right, particularly with DWB. MIPI is fairly well configured out of the box, but I still need to do some planning or tweaking of it.
A question about the 20 different trajectories that it generates. It seems like, when you get into like 8,000 and then it is those 8,000 trajectories, does each one of those have to go through all of the critics?
Yes.
So then you're talking like maybe another factor of 10 or 5 or 6 or something. It seems a little excessive if it seems like maybe a handful, 5 guesses would be good enough and pick 1 out of 5 instead of, 1 out of 20. What happens if you reduce that number?
Yeah, in fact, the recommended ones are much smaller than mine. What is this thing called? If we look down
The controller frequency or something in there?
What were they?
The X, Y, theta alternator parameters.
So I didn't show in this paper. In another paper, I showed you what the default paper. So I think the default XY samples, well, where it was down the bottom there. The default XY samples was like 20, I think, and the default VX was like 20. I think VY was like 10, and V theta was, I don't know, 5 or 10. I've got these because I've got a fast processor, and I want fast convergence on this stuff. So these things affect your thing so it definitely affects how long it takes to do this. They're not quite as important as the resolution of your cost map, how many squares there are in the cost map, but they're somewhat important. These algorithms are fairly fast. Each one of these critics, they're generally pretty quick.
Mike, I'm going to go ahead and stop the recording now, if that's okay.
Yep.
And you say you're going to get this. Can you post the paper to the